Hi, welcome guys. You're coming back into our class notes on the graphs of polynomial functions. A lot of this is kind of a conclusion, putting together a lot of the things we've learned in the prior videos. And so we're going to be working through this, and we're going to have some things for you to do on your own. So the first thing is going to be an investigation. You may use your calculator or you may use Desmos, whatever you have available to you right now. And so what you're going to do is you're going to graph the polynomial functions either on your calculator or on Desmos. And what we want to do is we want to pay close attention to how the function enters the view screen and exits the view screen. And what we mean by that is we're kind of looking at our quote unquote end behavior of the function. And so that end behavior is going to be very important. And we're going to tie that end behavior to the leading coefficient. And this is basically kind of the leading coefficient test. It should be fairly straightforward. I did go ahead and complete the first two for you, just so you could see what I'm looking at. And I'm a little lazy. So instead of writing out the words even or odd, I went ahead and I'm just using E and O, even and odd. For the first one, you see here in yellow, I have the 2 and the 4 highlighted. Those highest degree, the highest power, they're both even. So I put an E for that. The lead coefficient is in turquoise. And so the first one had a lead coefficient of 2, and the second one had a lead coefficient of -1. I'm just putting a plus or a minus for positive or negative. And then what we're doing when we do the actual end behavior, remember we're doing the limit. So we do the limit with the x going to -infinity underneath, and that is going to be the left end behavior as x goes to -infinity. And we're going to do that of the function f of x. So that's kind of the notation that we would have for that. And then the right end behavior, of course, you're just basically calculating the limit as x goes to infinity of f of x. And instead of me actually saying the words rise and fall, I went ahead and I'm using, math notation. It rises, we'd be heading toward infinity. And when it falls, it's going to be heading to -infinity. So rise, the limit is infinity. If it falls, then the limit is -infinity. Now, make sure that as you are graphing these and filling this in, that you are kind of zooming out as you are doing it, because you want to make sure that you include all the behavior of the graph. Partly what I want to look at for that is that if you zoom in too far, you may have a kind of bad idea of what the actual end behavior is doing. Now, let me check. I'm having a little technical difficulty here. So let me see if I can sync myself. I always love how it says the page is saved, but yet it's not actually saving the page. What happens if I click off and click back? See, there you go. So maybe I just have to do that whenever it gets stuck. All right, so if I think about this, suppose I have a calculator window. And in that calculator window, maybe I see this right here. And notice that the actual end behavior of the function is both going up to infinity, both the left and the right. But if I have zoomed in so that my calculator window is only viewing this portion of the graph, I may mistakenly think that the end behavior is both going down, and that would be a mistake. So we do want to make sure that we have zoomed out until that we see very clearly what that behavior is. All right, so you're going to complete this whole section right here, and then you are going to answer this question at the bottom, study the information collected in the table on the previous page. What general inferences can you make about the end behavior based upon the degree of the function? And I'm going to pop up a little open-ended question for you to fill that answer in. Okay, now that you've answered and come to your own conclusions above, let's see if you can fill in this chart, which is right below. Notice that I have put the 4 cases that we're looking at here. We have our odd both positive and negative lead coefficient, and we have our even, which is both positive and negative lead coefficient. And then what you're doing is your left in behavior, you're basically telling me what the limit as x goes to negative infinity of f of x would equal, either positive or negative infinity. And then the right in behavior, tell me that. So based on your information above and the two things that we know about the degree and the lead coefficient, answer these questions. And then I'll pop up an open-ended series of questions to get some feedback from you on this. All right, you can certainly check your answers so far using my key that is in the OneNote notebook and kind of see how you're doing on that, but hopefully we're okay. So we're going to look at the table for some graph functions below, and I'm going to do the first example, and then I'm going to leave the rest of them kind of for you to do on your own, because once I show you a little bit of what you want, this set of notes is really just bringing that together. So for example, here in this first one, we have a function. There's a couple of things that we would notice. We have a 0 at -3, and that 0 at -3 because it looks like a cubic and it changes sign and it crosses the x-axis. That multiplicity is going to be at least 3. We'll say odd, at least 3. So 3, 5, 7, and so on. But the min multiplicity for it must be at least 3. We also have a 0 at 1, and that just crosses like a line. And so that is going to be a multiplicity of just 1 as we are taking a look at it. The next thing we're going to have is the degree and the type of function. And again, we're looking at the min degree, kind of, in this idea that we're trying to give you, of course, nice polynomials to start with. So we want to make sure that we understand that there could be higher degrees on this in more complex polynomials, but we're just hitting the main basic types. So in looking at this, because I have at least a 3 multiplicity 0 and a single, and notice that both ends are going in the same direction. So I know that the degree is even and that it is at least 4th degree. Okay. And I think that should be enough in terms of that question. Type of function, if it was a 4th degree, then that would be a quartic. That's not as important to me, but the more important part is that it's an even degree polynomial. Now it says determine if the leading coefficient of the equation is positive or negative and justify your conclusion. I would say in this case the lead coefficient is negative, okay? And the reason is because the both end behaviors are going to go down. So it's an even degree with, and I could say in words, the end behaviors both fall, or I could say using math notation, which we do enjoy, with a limit as x goes to, and I'm going to do plus or minus infinity of f of x, the function, equals negative infinity. That the important part is both plus or minus infinity are both heading down to negative infinity. So that would mean that the lead coefficient is negative. All right, I'm going to leave each of the next 3, the last one on page 2 here, and I'm going to label these so that when I refer to them in the questions, you'll know what they were. This one was A, this one was B, we'll call this one C, and we will call this one D. So go ahead and try this one first on your own, and then I will pop up a question on that one. And then you're going to go ahead and do C and D. We'll just do this on your own and go ahead and fill in the question that I pop up in the video. So I'm going to pause and I'm going to let you guys work that and then answer those questions. All right, so hopefully this is all pretty straightforward for you guys. We're now going to kind of go into the next example. This is going to be, we kind of looked at things graphically. Now we're going to look at things a little bit more numerically by looking at the table of values. Now, some important things that they're giving you in the stem of the problem is that it's quintic, which means that you have a fifth degree polynomial, which hopefully is telling you some information about the function. The zeros in the table are going to be the only zeros of the function. So I'm going to kind of highlight that. So that means when I look for the zeros, I'm going to highlight it in yellow, I believe. So let's highlight, there's 1, 2, and so those are the only 2 zeros. And even though I did not say this in the stem, in pretty much all of these notes that we're looking at, we're going to assume no complex zeros, okay? No complex zeros on this at all. So the fact that there are only 2 zeros means that there's going to be some multiplicity on those 2 zeros, and we're going to use the information in the table to help us determine that. All right, so the first thing we're going to do is determine the left and the right end behavior of the function. Now, because we know that there are no more zeros, we can't turn around again and go back through the x-axis. That means that we're going to be staying wherever you are on the ends. So when I look at the ends of the data table that I have over here at 6, -6, -147, and 6 to 25, that when we are looking at that, we can't turn around and cross the x-axis again. So what that is going to tell me is that the left and right end behavior of the function is pretty much set. That the left behavior, and again, I'm going to use the limit notation because that is what we want to be using. So the limit as x goes to -infinity of this function, whose name is capital F of x, must be going down to -infinity because I can't cross the x-axis again. And then the right end behavior, the limit as x goes to infinity of f of x, that one, because it's positive 225, must be heading up to infinity. So that takes care of that for us. Now, based on the end behavior, what do we know about the degree of the function and about the sign of the leading coefficient? Well, we already know that it's a quintic. So it's a fifth degree, which is an odd degree. Okay, so we're odd, and that makes sense because notice our end behaviors went in opposite directions, and it's falling on the left, rising on the right. So overall, it's a positive trend. Even if it goes up and down in the middle, it's a positive trend. And so that tells me that we have a positive lead coefficient because the left, I already wrote the limit notation, so I'm just going to use English now, because the left falls and the right rises. Okay, and I'll just do overall increasing function. And that might be a bad way to say that because it's not increasing the entire time, but it's increasing kind of if you squint at it and look at it across towards the end. All right, identify the zeros and the multiplicities of each zero. So we only have 2 zeros. We have -3 and 1 are going to be our zeros. Now, in terms of multiplicity, remember that the sum or the degree has to be 5. So we know that the only way that we're going to get to that is if we have one that's a single degree and maybe one that has a degree of 4 or a 3 and a 2. We have to have some combination of this. So I'm going to look first at the -3. And what I'm looking at is that before it's negative, and after it's positive. So if I'm just looking at that behavior that you have, and also the idea there are no more zeros, then we know that we have changed signs at that. So we know that it must be odd multiplicity. So -3 must have odd multiplicity. And the 1 must have even multiplicity because it's positive and positive. And remember, when we can't cross anymore, so this is pretty much it. So this one's going to be even multiplicity. So there are really 2 options kind of as I'm looking at this. Option 1 is going to be that 3 has a single multiplier